it's 9:10. Let's start. And give me a second, I'll set this up. First thing is to update you guys on this one, which is the assignment 3. And I just opened it, if you haven't seen it yet, but I don't know what's available or not. But now it should be available if it wasn't. And this is the assignment, and the assignment is very general, so it's very unlike the other two where it's a bit more structured. Assignment 3 is quite open. Of course, there's a guided, very minor guided part at the beginning, but really the key part is option 2, which is optional. So like if you do, you have to do question 1, and that's basic, but it would be great. But it'd be great if you can do option 2 and see if you can push your boundaries a little bit. And so just to guide you a little bit first, assignment 3 obviously is about the unsupervised learning using the von der Mausberg network. And you will see that unlike the others, I haven't broken it up into like first create a model, first do this, first do that, and all that. The reason is this, okay? For the other 2 papers, the idea was you read the paper, and then we give you some exercises. I break it up, and in doing those exercises step by step, you are actually recreating the simulation in the paper, okay? And a key part of that was you didn't have to digest the paper and then kind of take out the components yourself to replicate the simulation that the paper did, right? Because that's what I did for you in the assignment is I took out those parts and tell you to first do this, and actually that's like some parts of the methods of the paper, like this parameter or these number of codes, right? So I kind of like, you read the paper and then I help you digest, or the assignment help you digest and break parts in, and then you run this thing. Is equivalent to replicating the paper, okay? Those papers. Here, do it yourself. See if you can do it yourself, okay? Read the paper. Very difficult already. So that's why I say if you can do 1 already, no questions asked. It's perfect, okay? And of course, I'll go through the lab with you today so you can sort of do 1. But I'm not going to define too many things, unlike the other assignments. I'm going to leave it very open to you for you to read the paper and see how and where you can replicate it on your own with minimal breakdown or guidance, okay? Because in real life, that's what's going to happen. You're going to read somebody's publication. It's going to be some modeling paper somewhere. Let's say you want to do some modeling work. It's going to be some modeling paper somewhere. And it's not going to give you an assignment to break down things. You're lucky if they give you a tutorial and then they let you have the tools and then you try it out. And that's how we teach. But in so-called professional or full-time science, they're not into it to tell you, tutorials to break things down. They write the paper, they put it out there, and it's up to you as interested scientists to read their paper and to figure it out on yourself, like how to replicate, or what are some things that you need to do to get to, where you can use their tools. You understand their tools and use it. So with the von der Mausberg exercise assignment, you're gonna read the paper, and I give you this open question here, the general question, plus what we'll go through in the implementation today in the code, and then that's it, okay? The idea is, the final thing you should do is replicate von der Mausberg's paper to the best of your abilities, okay? Now, of course, I do not expect you guys to totally, replicate everything or do everything. Some of you can, maybe if you can, that would be awesome. But the goal here is not to have perfection, okay? Otherwise you can publish papers already, right? But to move towards that direction and try, get your feet wet, try a little bit to, so this is what it's like to replicate maybe figure 1 or figure 2 or whatever result that von der Mausberg has. This is what it's like to replicate up to that point. and then maybe some parts you can't replicate or you know don't get there, that's fine. But try to see how far you can go. You should at least be able to replicate the first part where we'll see today, where the network shows you the what we call the spindles, you know, the clustering after it's been trained, right? Selectivity, okay? So that's the first part. Any questions about this one first? Okay, no? If you come back to it and then you can ask more later. The second part, you will see that I mentioned this MNIST stimuli. And if you don't know what that is, I can show it to you first. It's an open data set. There's no preview. I guess you can look at here. Oh, it's not here anymore. Maybe Lacun deleted it. Let me see. Well, yeah, it's here. You can download it. But I was wondering if they have a figure or a picture of it. If they don't, I guess this one should have. Yeah, here, something like that. This is the MNIST database, which is basically handwritten numbers. So 0, 1, 2, 3, handwritten digits. Okay? And the idea here is that there are 10 different digit types, right? Can we get a self-organized neural network to, you know, process this, to respond to this? And if so, what would the network, how would it behave? Because imagine that there are horizontal, vertical orientations. So in the simulation, in the replication, we will do the hexagon and the just basic, very simple horizontal lines and how it rotates. How would that translate to a more real life thing where, you know, life is not just very simple lines, life is complicated? How would you change or modify your VDM model if you successfully make it? How would you modify it so that it can, and then do something fun to demonstrate how, you know, some concept that you might expect the model, if it is selective, to be able to do that. Okay, so try that out. By the way, this is real human writing. So, you know, Jan LeCun, who, like, I think he worked for Facebook or he helped Facebook a lot, did some, you know, just wrote things, and the question was, hey, can we even get humans can recognize it, no problem, right? Obviously. But for a machine, actually, it's not so easy, right? So that was an ongoing problem. Like, how can we get a machine to actually do what humans do when we read? Clearly, we know all of these are sixes, but to a machine, they are not all exactly the same. How do we get it to recognize that it is all six, right? It's all six. So some level of convolution must be involved, meaning that it must have spatial invariance. It doesn't matter if the 6 is big or small or here or there. Somewhere there is a 6, right? We know that. We perceive that. So how do we get the machine to do that? The argument here is your VDM, which has some convolution going on, might be able to do that. However, it is not trivial. Okay? Let me just say that to really solve this is not so trivial. You really have to tweak your model. I'm not going to leak it out. It really is a PhD and higher level kind of question, but let you guys have the opportunity to 伤脑筋一下, you know, rack your brains and then get inspired to, oh, I can do this. I think that experience is precious, so I won't rob it from you, okay? But I can tell you it's not easy, it's very difficult, okay? All right. So it is optional, and but I put it there as a challenge for people who want that challenge. Already, number 1 is already very challenging. So that would be assignment 3, okay? So assignment 3 is not trivial, and it is due on June 19th, because I have to submit the grades by June 22nd, I just checked. So a week before, let me have time to go through your assignments. But it's due on June 19th. So you have, now it's May 29th, so you do have about 3 weeks to work at it. Okay. Next week, your assignment 2 is due. But I'm going to assume that people don't have problems up to this point with 1 and 2. I've seen some of your work. I think you guys can handle it. So just submit assignment 2 and start working on assignment 3. I think it's fun. And of course, we'll give you guys the push today. Like I show you the code, and you can see how you want to use it or implement it. Okay. Any questions about assignment 3, von der Malsberg? All good? Okay. Go back and read the paper again and again. I can tell you that I've read von der Malsberg paper probably more than 50 times or something, I'm sure. Something like that, along the way. Because every time I read, I see something new. And then I realize, oh yeah, then now it makes better sense. Like the first time I read it, nothing makes sense, right? Then second time I read it, every time you read it, some parts make more and more sense. So it is likely you're going to have to read the paper quite a few times. You guys are lucky. You have AI to help you interpret things. Last time we didn't have anything. It's like you don't understand it means you don't understand it. And then the only way to understand that if you want to get to your teacher is like during class and all that kind of thing. I mean the traditional stuff, right? So now that we have Google, internet, and all that, maybe it'll be easier for you guys to get this really quickly. Because a lot of YouTube clips out there to help you to explain things in different ways. That different people will get the insight suddenly. All right? Okay, so today we will talk about the unsupervised learning using this Jupyter notebook. So if you haven't, you can open it. And I'll go through the code. And today it might be actually pretty fast because you're just going to go through this code. And then that's it for today. And this code is actually as complicated as VDM is. The code structure is quite straightforward. Because the most difficult part is not the VDM itself per se, but the setting up of the hexagonal system and using it, like integrating it into a code that expects a grid coordinate system. As in, if you do neural network, right? It's like you have arrays, right? A 2D array is an x, y, or an ij index, right? So it's like if you loop, you'll be doing for I 1 to something, or for I 0 to infinity, and then for j 0 to infinity, you do these 2 loops. You are cycling through the array. But in the hexagon, it's not just iterative. So there's a transformation. So that's always been the tacky part with VDM. But then that's the nature of it, of the challenge of what we have to do here. Okay, so this notebook implements VDM. You can read the paper. You must read the paper. And the goal of VDM was really to simulate a V1 neural patch. So the target in V1 in VDM is actually the V1. So it's the cortical layer. Right? So if you remember back to your notes lecture last week, the target that we want actually is about the activity of the AE layer, okay? Not the AI, not the inhibitory layer, actually, and not even the input, the small I layer, but the A big E layer, the excitatory layer. That is supposedly the target layer that is of interest here. For VDM, what is the AE layer? How does it behave? Okay, so that is the so-called problem definition here. Of course, given the input, given the AI, but then the point is we want to see how the AE behaves. Okay, so an AE meaning that's the V1 neural patch. that takes line orientation inputs from a fixed location in space. So what is being simulated here, and again, if you read VDM very carefully, you understand. It's not that the network is trying to look at the whole scene. A lot of people get tripped up here. We think that it's like trying to see a whole scene and then we see lines there. No, no, no. Actually, what VDM is trying to do is very, very specific. It's only caring about, let's just care about this location in space only, just this location. How does the whole V1 or how does a patch of V1 respond to just this place, right? Obviously, there's a whole scene of many, much more information, but for now, VDM is not caring about that. It's only caring about one dot in space, one point in space, and if you all know V1, if it is here, then it is likely in my right side inferior, V1 cortex tissue location, right? Because it's like that, 就对称的, okay? So, and if it's periphery, it's like that. If it's fovea, it's like that, okay? So, doesn't matter where, but let's just pick one location. And the question is, and then there's a V1 patch there, which are the AE layer. How does the V1 patch respond to when in this place there are different line orientations? Okay? So, and the V1 neurons patch, let's say there are 169 neurons in this V1 patch. All of them receive input from this location, this same location here. So how do these 169 neurons in this V1 very small patch here, but there are 169 neurons there, how do they as a ensemble, as a group, respond to one location having different orientations? Okay, so that is the definition. You have to frame this very clearly. Otherwise, if you make the mistake, you think that, oh, he's talking about a whole thing, and he's talking about the whole V1, you will find that no, that won't fit exactly, okay? You want to do the whole thing, you want to do the whole V1, that's sort of like the MNIST problem. You have to change the architecture from this base, but you have to expand it a lot, okay? So that is we have to frame it in the biological constraint. That is what the VDM model is targeting. One location in space and a small patch of V1 neurons that receive this as the input. How do they respond to the changing inputs in terms of orientation of the lines? Okay? All right. After training, each neuron in the V1 patch exhibits selective response to specific orientation. That is what we want to replicate. How do we make this patch exhibit the selectivity that we see in the biological observation? Like, oh, I guess he did it with tree shrews. Well, Huber and Wiesel did it with cat and monkey. Okay, so there's these papers, references 2, 3, and 4, which are real experiments done that we know that in mammals, at least, with visual systems, we see these selective responses and what that means, how that looks like in terms of the empirical data. So we are trying to, or VDM is trying to replicate that, okay? So what is being replicated would be the selectivity in terms of orientation and a spatial gradient manifold of different orientation selectivities across the surface, which is, again, what we talked about in lecture last week, that if you were to follow along, if you were to kind of have an electrode and follow along a line on the surface of the patch, it would be, this one is sensitive to vertical, this one, the next one, the neighbor will be slightly off, side off, side off. If you just follow along, you kind of almost replicate the rotation like that. That is the gradient of orientation manifold. Manifold meaning a plane, like a surface, right? A kind of a space that defines some sort of changing property, okay? All right, so this is the overview. And let's get a bit more formal here. So the idea here is to make an ANN, an artificial neural network, show self-organization for clusters and gradients across columns, okay? Functional activity of neurons in the brain exhibit organizational patterns, blah, blah, blah. I'm not going to talk about this. You can read it. I think the key, we talked about this last week. This is all the theory before. So if you want a quick review, just read through the sentences. The key thing here is that the architecture will be such that we have a retina that feeds into a patch, of V1 neurons from the retina, okay? So 19 units to 169 units, right? And then there's also a layer of inhibitory connections, also 169 units, the AI, okay? And that is mimicking the GABAergic interneuron, or some people now say basket cells, or GABAergic basket cells, or whatever. This is very, very, we are now much more advanced. We know, there are more cells, but this basic neural architecture remains. That there are excitatory neurons and inhibitory ones, and they are interdigitated in the V1. Okay? All right. Let's see. Okay, yeah. So we have this architecture, standard autoencoding learning rules, as we talked about last week, right? Actually, it's implementing autoencoding in the weights updating, right? If you remember. And the activation function is ReLU. And we know that ReLU has a problem. It goes to infinity. So there's a normalization step as well, you'll see, to kind of shrink it back, okay? And so the idea is to see if we do this somehow, put it together, it will show self-organization, okay? Very cool, all right? Yeah, so many things to read. And if you guys really like this kind of thing, if you enjoy this kind of thing, which I do, you spend time reading it, and I think it's fun. It's very inspiring, okay? All right, what's the data table? So as we talked about also, just to remind people, the key distinction between this exercise or this model and the other two that we've talked about is that the binary word positioning, the element position, the position is not arbitrary. The position and their relationships, to be specific, their relationships are not arbitrary. In the Hopfield and the backprop that we did, you can have the binary, unit 1, 2, 3, or 4, or 5, as long as in general their patterns are orthogonal or not orthogonal, or overlapping or what, as a set, between sets. That's all that matters. Whether you do that orthogonality or overlapping using unit 1 or 2 or 3 or 6 or 8 or whatever, doesn't matter. It can be 1 versus the infinity position or 100 unit position. It's the same as 1 versus position number 2, as long as those have orthogonal activation states. Here, it is not arbitrary. 1 to 2 is closer than 1 to 100. So even if the two are orthogonal, or you have orthogonal sets, the orthogonality is only one part of it. It has to be that the orthogonality is being done in the neighbor or in a faraway neuron. That makes a difference as well. Okay, so the distance, the position, the relative location of the units in the input bit binary word is not arbitrary. There is spatial encoding. Okay, so that is the key fundamental and the most important thing to get that distinguishes this from all the other networks. And I would argue to a certain extent how LLMs operate now as well. LLMs right now operate, at least when it comes to taking in words, like text, are like the Hopfield and the multi-layer perceptron that we've been using, where the bits locations are essentially arbitrary, okay? They have integrated LLMs with CNNs, convolutional neural networks. We'll talk about that maybe at the end when we have one free lecture or whatever, where convolutional networks, where VDM is one of those, is the space, the location is not arbitrary. So they have integrated CNNs with LMMs to kind of give LMMs a sort of a sense of space as well. But the real driving engine, the LLM part, actually doesn't care about the space per se. Okay? So a lot of it is very abstract concepts. Might be floating over your head. Okay? But just to let you know, this is how, once you understand how these classes and categories of networks and what's going on, you will know, like, yeah, what are the limits of each different kinds of networks. So that's the key distinction. Location positions in the input are not arbitrary. The input position has meaning. The relative position has meaning. Okay? So you can do it in a circle or centroid. In digital format, we're going to use hexagons. So in real life, obviously, our eyes don't see hexagons. Our eyes see very continuous, circles or radial light. Okay? But in a digital, where you have pixels and quantized position, which means categorized and bin positions, the hexagon is the closest equivalent to a circle. Okay, so we use that as an approximation for real life. Okay, so to do that, we first have to do this hexagonal node array transform function. So this is what we'll do. Okay, so code proper. First, we import modules, and as I said, I like Plotly because I think Plotly is a lot more interactive than Matplotlib. Feel free to use whatever you want. Plotly also has limits. Sometimes it's overly complicated. It's also very resource intensive. Compared to Matplotlib, it's very light. But because here, I think resource-wise, it's not an issue for what we are trying to do, Plotly gives us very nice interactive things you see. Okay, so set up some modules. I use Plotly graph objects, Plotly subplots. You see why? Because then in one plot, I can plot many subplots. And obviously, we need NumPy. I took some inspiration from, well, originally I didn't. But recently, because there is this resource, I found it. And is it there? Oh, it's still there. Good. It's gaming people. Okay. In game world, I don't know if you all play those MMPORG, whatever it is, those massive online worlds. It's graphics, right? It's really just graphics. That's why we need Jensen Huang for all the NVIDIA GPUs. It's just so we can play games in virtual space. Right? And then pay money. This is a fundamental problem in games, because games are trying to give us the visual world, but in digital format, right? So we just said, in real life, it is circle, but in digital world, it's not, right? It's quantized coordinates. So hexagon, the fundamental hexagon transformation is a fundamental thing in all of those computer game things. Okay? So look at this page, and you have a lot of mathematics. You can spend time to go. There's different ways to code it, and if you understand it, essentially the math here, so here, okay, there's some math here is what you can see will be implemented here. Okay? So you can spend time to go and see this because it takes a while to go through the geometry, but what it is the hexagon is defined by, at least if you understand the hexagon, there's two ways to do it. There's a flat top way or a pointy top way. And you can see that depending on which way, because it's rotating, then you want to use your base unit, which is the size, because this length is different from this length, right? I hope you can see that, right? This length is different from this length. This length is this length, right? So, but if you rotate it, then it's the other way around. So if you have this pointy orientation, then the centroid is defined by this, and then half of the short, and then half of the short, like that, right? So you can see how on a Cartesian grid, which is the underlying square grid, that if you have a hexagon, the centroids are located like relatively like that when you overlay it on a Cartesian grid. However, if you rotate it, I think you can do flat top here. So cool, right? Then it's different. Excuse me. Okay, Note that here, it's like, here is one, every step is half a Cartesian unit, all right? Or you can say one Cartesian unit, but then twice, right? You can, it's just scale. But basically, the hexagon unit is not the same as the Cartesian. Just, but obviously you can align them on top of each other, and then you use that trick to transform between the Cartesian coordinate and the hexagonal coordinate. So in other words, if I have a flat top hexagon, which is what we will use in von der Mossberg, if I want to identify the location of this point, this point is equals to, relative to here is 1, 2, 3, 4 by 1, 2, 3, 4. So Cartesian 4, 4 is hexagon unit 1. Cartesian 6, 4 is hexagon unit 2, correct? Okay, and okay, this line is not good. So if I want to go to here, this will be Cartesian unit 3 and 3, right? And then this will be, but this is unit number 1, 2, 3, 4, 5, 6, or something like that. You have to see how you want to index those points, and then you'll know that if I want to turn this on, if I want to turn unit 1, 2, 3, 4 on, then I need to know that unit 4 is actually Cartesian unit 3 by 3. Okay? Actually, it will be 3.5, not 3, right? Because this is half. 2.5, not 3. Okay? So translating between Cartesian and hexagon coordinates to index your hexagon units so that you know which one to turn on and off, effectively meaning turning on and off that hexagon location. Okay? So I put this thing here because this, I think, helps us to understand the geometry better, because you won't really get it by looking at this code, but this is what the code does. Okay? So define, the very first thing is to have a way to create hexagonal grid points. Meaning, like, I want to have a way where I can translate, if I give it some row index, some column index, and the spacing information, which is this one, okay? This spacing information. Because it can be, I want a big hexagon or a small hexagon. And incidentally, this determines the, in the VDM code, remember we said how many distances apart the neuron will excite or not excite, will inhibit or not inhibit, right? So this is a scaling factor to match with, what is the radius we want for the neuron's influence. So we want to have this code that will tell us that if I give the number of rows in a grid and the number of columns in a grid, then, and the number of spacing distances, then I can have a whole hexagon grid system. You'll see how it's done later, okay? So this code does that. So it takes in, first creates a blank, empty XY output, okay? Nothing yet in there. And then defines a kind of a scaling factor which is basically half of the spacing times some tangent thing. This is trigonometry, okay? Because you need the hypotenuse. That is the hypotenuse, the triangles, the slope part, right? Tangent of the two opposites. And the degree is 60 because it's a hexagon. 就是这个角度是60度. So that you can know the 那个斜度的那个长度，斜线的那个长度。And then go ahead and calculate for the whole grid that you want, what are the XY locations? So in other words, what is this XY coordinate? What is this XY coordinate? What is this one, this one, this one, this one? All of these black dots, what are all the coordinates that define this hexagon space? And more than that, it will also calculate this black dot. Here they don't show it, but there will be a black dot here, right? And there will be a black dot here, right? And here, and here. right? And then maybe there'll be another one here and here. So a whole, for a given space, you will define all the hexagonal points, vertices. Okay, so this is what it does. And then I need a way to plot it, to turn some of these coordinates on or off, correct? So I will take the xy coordinates that I have generated with a hexagonal world, and I will have an on list that says these are the locations that I want on. The rest are off. And I will have subplot, subplot, subplot. All this is because I may want to do more than one. You'll see later. It's not just I want one, I want a few of them. So I have for every subplot, find x where it, and whether the x matches an on list, and then make it equals to 1, right? And the y as well, all right? So this is what this does. Units that are off are where it's equals to 0, and then make it small. So make the on units size 10, make the off units size 3. So it's I still mark it. It's not blank. I still mark it, but it's smaller because that way we can see the hexagon that some of them are on, some of them are off. Like that. Okay, that's what the visualization is. And the rest are just formatting. Okay, so, and now we can go ahead and visualize the manifold, the hexagon manifold. So I want a hexagon space that has 8 rows and 29 columns, all right? And the spacing is just radius 1 for simplicity. The on lists are empty ones of number, grid rows, and grid columns, meaning I want this all the hexagon to be, all the dots to be on, to visualize the space, right? I want to see the whole thing. And I only want one plot, one hexagon, or one hexagon shape. All right, and then I plot it, some labeling, and then I use the create hex grid one, the one to create the coordinates in Cartesian coordinates. And then I tell VDM hexplot to turn which of these coordinates on or off. And the result is this is what this code will do. Okay? Any questions here? You can see it is overlaid on a Cartesian space, yes? You can see the underlying grid, square grid, which we are used to. But it is selecting certain coordinates in this square system to turn on and off selectively in this sense. And because of the calculation of which coordinate we want, which is a hexagonal calculation, the one that we use this one, right? These equations to determine the coordinates. Then when you turn those vertices on, and you visualize the whole thing, you see that it is hexagonal in nature, right? I hope you can see, right? I'm sure you can see, okay? Okay, a key thing, and it's this one I spent a lot of time. I remember when I was doing my first code, I spent a lot of time having headaches, is because one thing you notice, okay? The difference between the grid, Cartesian grid, apart from the hexagon shape, of course, and the hexagon system is that every row and every column is like shifted like this. Whereas in a normal grid, it's like, of course, you know, you just iterate every row and then every column is the same. But in a hexagonal world, row 1 has fewer nodes than row 2, or columns has, you know, like whatever, different. I mean, you can cut it this way. So this is why this is flat. So, and that's why this is another headache. It's flat means this will have fewer nodes than this next row, and so on and so forth. But if you do point, then it will have the same number of rows, but it will have different number of columns, that kind of thing. So it's very irritating. Okay, spend a lot of time headache about that kind of thing. Yeah, but it is what it is. It's the hexagonal world. You stare at this too long, you might get optical illusions. So, and you can play with it, you can make different colors. It's very fun. Yeah. Okay. All right. Okay, then we can play with it now. Now we want to define, let's carry on with the code. Now we want to define the stimuli, okay? So you see now, I want to have a grid row of 3 by 9. So 3 rows and 9 columns. Yeah, so part of the headache is determining how many rows and how many columns you want. So here, you can see 8 rows and 29 columns will give me this kind of thing. Because you know why there are 8? So it is, I think it is 1, 2, 3, 4, 5, 6, 7, 8. Every 2 rows is actually 1 Cartesian row. Every 2 hexagonal rows is 1 Cartesian row, because actually 1 hexagon is 3 rows, 3 sub-rows, right? And then, but equivalently, actually, there are 29 columns. You will see 1, 2, 3, 4, 5, 6, 7, 8. So that's why things are very counterintuitive here. So if you count that and you realize that's the number scaling difference between going rows by columns, then you will see that that's why here, to do our stimuli of 19 units, we need 3 rows and 9 columns to get 19 units in a hexagon that we want. You'll see. Okay? Keep the radius as 1. And we have a select array. These are the this select array is basically to define the 19 units. So you'll see that there are 19 unit 2 in the whole array of 3 by 9 columns. I only want to work with unit 2, 4, 6, which is going to be the hexagon 1, 2, 3 like this. Okay? And then 1, 3, 5, 7, 9. And then 11, 13, 15, 17. And then 10, 12, 13, 16. And then 20, 22, 24. I might have done it the other way. Okay? Yeah. But so there's 19 units locations here. So there are 19 numbers here. Okay? And then for that number, for unit number 2, I want it to be off. For unit number 4, I want it to be on. Okay? For unit number 6, I want it to be off. Okay? So this is actually my input data table. And I have, by hand, okay, made it on or off. And you see here, it doesn't make any sense, right? To you, the ones and zeros here, you look, it's arbitrary, right? It's just a 19-bit word, just like the input from the back prop and the op field. But these on and off states are credited, assigned to those 2, 4, 6, 1, 3, 5, the selected points on the 3 by 9 hexagonal transformation system. So that if you put it together, and because there is a 9 different patterns, so 9 rows of the input, so I'm going to plot these 9 different patterns as a 3 hexagon by 3 hexagons. So that subplot n rows 3 by 3. Okay? And then the rest are labels. If you plot this out, these are the van der Waals-Berg things. Okay? So you'll see. This is, oh, I hate this cursor. It's so big. But this is 1, 3.46, 2, 3.46, 3, 3.46. This is 1.5, 2.598. Okay, these are the Cartesian coordinates based on that calculation that we had, the 3 over 2 pi cosine, well, all those. So what the Plotly is giving you in the highlight there are the Cartesian coordinates. Okay, so these coordinates are, when you turn some of them on, some of them off selectively, because we've identified the coordinates that we want, we'll define a hexagonal pattern. Okay? And there are 19 units, and then I select to only work with 2, 4, 6, whatever. And then in position 2, I want it off. So you see, to make it even more clear, 246, let's take the first three. 246, I want it to be 0, 1, 0. What this means is, I think this one is 246, the bottom. So 0, 1, 0, I hope you can see. 0, 1, 0. Oh, this cursor is really irritating. Okay? I guess I should use this one. In case people can't see. Okay, yeah. 0, 1, 0. Okay, 2, 4, 6. And then there'll be, the next one will be 0, 1, 1, 0, right? So I hope you can see. 0, 1, 0. Then the next one is 0, 1, 1, 0. You see? Then it's 0, 0, 1, 0, 0, 0, 1. So it'll be 0, 0, 1, 0, 0. See? Got it? So that's how you can make it such that by identifying some order of units and combining it with your Cartesian hexagon transformation, you can create these things like that. This is by far the part that made me spend the most time of the whole thing when making this simulation, because it was so, I have to put so many pieces, because the paper doesn't tell you how to do it. Okay, the paper tells you how to create the model. The paper doesn't tell you how to create the hexagonal grid system, so I had to figure it out a lot by myself. Last time, no internet. We go library and borrow mathematics book to say how to do this. It's very painful. And there's no PDF, it's photocopy. Yeah, I remember I have nightmares in the Illinois library. Any questions? I've done it for you, so you have a great time now, but I hope you can have fun with it too, okay? Okay, so this is to instantiate the data table, and once you have the data table, we can move forward to the creating of the model. Let's take a break before we do that. Now it's 10 o'clock. How about we come back in 10:15? Let's take a nice, it's relaxed today, so 10:15 we come back. Okay? All right? right. Okay, let's pick it up again. See if we can finish this in an hour or so. All right, so we've got the stimuli. Okay, so now we have to create the architecture of the network proper. And again, I had to do this by hand after you do some calculation. And there are 169 units. I have to mentally think, what are the, in the whole, if I want a grid, like how big, which in this case is 8 rows by 29 columns, which of the coordinate units do I want to define my AE activation units? 169 of them. Okay? You do some simple hand counting, you will know that basically these are the units 7, 9, 11, 13, know that. Then 35 to 51, 34 to 52. You can see the shape already tells you it's a hexagon because it's like, you know, first row has 1, 2, 3, 4, 5, 6, 7, 8 units. And then the middle row has, I remember, probably 15 units. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yes, my memory is perfect. 15 units and then 8 units. So 8 to 15 to 8, and it will form the hexagon. Okay? Yeah, I had to do this by hand. If you guys can create, as in, of course you can do a code. But I was thinking so much about the code, and it took me so long that I just do it by hand. I do it in one day. If I do the code, it will take me, I don't know if I, how long, I don't know. But of course, this is a one-off thing. You do it by hand, that's fine. If your career is having to need hexagons and all the time, then I suggest spend more time doing the code. Okay? Don't do this by hand all the time. All right? Okay, so if you guys have tools that can do it like automatically, you know, using this and all that, of course that would be very welcome, and feel free to suggest to your classmates as well. I'm sure they'll be very thankful because then they can play with, remember, if you want to expand, maybe having a code to do that would be part of it being helpful, okay? All right, so this one is, again, some labeling and beautifying things. But essentially, you will get, this is the E layer, 8 activation units, 169 of them in the excitatory layer of the cortical tissue, the cortical layer, the excitatory part of the cortical layer, okay? And similarly, because the E layer and the I layer are the same size and definition, actually the E layer, you can copy it and it becomes the I layer as well in terms of the array setup, all right? So now, so that is the base architecture pieces that we need. The next thing would be, of course, to have the training function. How are we going to train? All right, so what's going to happen? We have a function called VDMU learning, which is the training part. And it's going to require, as usual, an initial weights array, which can be uninitiated, untrained, or it can be a trained one. So W can be a kind of a nothing kind of setup, or it can be a pre-trained W set, whatever the architecture is of W. Okay, P, R, Q, S, H, T, all these are the hyperparameters you will see in the von der Mausberg paper, which are the distances, so separation, then some normalization, you know, the normalization S, or the cache thing that we had last time, the radius we want for the inhibitory units, the radius we want for the excitatory units, and the threshold we want for the ReLU, and all these kind of things. So these are the hyperparameters. You'll see them being used later on. The order is the, I forgot what the order is. E set order 1, 0, 1, 2. Oh, It'll come to me when I see it, okay? But we have key thing is we have an input here, which will be the input or line orientations, and I believe the theta is the threshold. Yeah. Okay. So how does this work? If there is no W, so if there's no pre-trained array, if no trained array, then let's set up the array, the W array. And what would the W array look like? Well, we have an initial kind of, these are the separating in terms of like, oh yeah, so how many units apart or something, I guess, in terms of like the separation distances between the units. I will come back to this later because I'm still not sure about what order is, how I coded it, and it will come to me when I see it implemented later. All right, so just like the above VDM hex plot thing, we have to tell it how many rows and how many columns you want in order for it to set up the array, the weights array and the input and the E layer and the I layer array. Yeah, I think, yes. Okay, it's coming to me now. If there is no input array, no pre-trained array, then order tells us which layer, how many units in each layer. So order 0 maybe has 100, I want to say 169 or how many units in each layer, so that it will use these initial information to build up the array. This will become clearer as we go along, but that's what these general parameters is to first get some indices about the sizes of the arrays that we want to create the architecture of. So grid rows would be W1, whatever was in W because it's untrained, so W1 creates tells it about the size of the rows and the size of the columns, and the spacing we set it to be 1. And so with that information we can create the grid rows in the hexagonal to the Cartesian transformation, and this is the same thing as I had before just now that gave you this, okay? All right, and so then we initialize input excitatory inhibitory layer connection weights, and in this case it is going to be random uniform from Ni to Ne. So Ni to Ne is basically the shape of the number of units we have, okay? So 169 to 19, 19 by 169 random uniform numbers that range from 0 to S. Okay, so that's what this is. So you can see this is going to be 19 by 169. This is WIE. So if you remember, it's the 19 unit to the excitatory layer, which has 169. So 19 to 169, this is the W small I-E array. This is the one that needs to be trained. Okay, that's why it started out as random, and then you shape the random into some constraint to fit the whatever orientation you want. Okay, this is the recurrent excitatory layer connection to itself. So it's 169 by 169. The initial state is that all of these are zeros. Okay, and similarly we have all these. Effectively, the arrays are the same size, all right? And so we just do copy. I mean, we can also do zeros if we want, but just do copy. And it has to be WEE.copy because, again, remember with Python, if you just say this is equals to that, it literally just labels it as equals to that. And so if you change the subsequent, if you change WEI, it will change WEE as well. If you just say WEI is equals to WEE, changing WEI will change WEE. But if you do WEE.copy is WEI, then it separates it. Okay, it makes a copy, but it is a distinct index. It's a distinct object. Okay, so then we have also a kind of cortical inter-unit distances. These are like, what are the distances between the two units? Set it up to be 0 at first, and then later we will be filling it in. Okay? All right, so then that is to set up the 19 to 169, 169 recurrence, and then 169 to the excitatory to the inhibitory, which is also 169 by 169, and the inhibitory to the excitatory, which is another 169. So you get basically these connections. Okay? Architecture, base architecture is set. Those are the pieces. Then we have to apply those hyperparameters, which are the distances and the spacing and the distances and the spacing and the weights exactly that we want. So for, this is where it gets tricky, for every unit 1 to every unit 2 in the number of excitatory units that we have, okay, the distance between two units, dy and dx in Cartesian space, is going to be equals to y of the y of the select, which is the vector that tells you which unit of the 169 hexagonal locations that you want, okay? So that unit 2 is maybe this hexagon unit, unit 1 is this hexagonal unit, okay? So the y coordinate is the difference between the Cartesian locations between these units, right? And also the x, right? The x. So that if you have a radius, so if we go back to the hexagon, it's easier to see it this way. So let's say this is u1 and this is u2, then the y coordinate distance difference, this is the x coordinate difference, and obviously the y coordinate difference is 0. But here, there will be a x and a y coordinate difference here as well, right? If you look at the triangle. So if this is u1 and this is u2, then there will be a dy by dx, which is the difference in the x and y coordinate. And you can use that to calculate the distance between, right? The distance between the two uy and u2. So that's WEED. So those are the distances of every excitatory unit with every other excitatory unit, right? Square of the two difference, square of the dx plus square of the dy, square root it. This is basic trigonometry. Will give you the distance between u1 and u2 in the Cartesian space. So now that you have the distance, you want to encode it, right? Because you need the distance to decide whether this is a unit you want to be influencing, or is it too far away, it's not influencing. So the distance will be encoded in WEED here. Okay? So distance between u1, u2 is equals to the square root of the sum of the squares of their two coordinates. This one okay? All right, so now we have an array of inter-unit distances. Okay, initially it was 0, but now we have some values in them. Okay, so we need that because then we know to say whether this is a unit that influences me or no, it is not relevant to me. So once we have that, okay, then for excitatory to excitatory connections, von der Mausburg says that the excitatory to excitatory connections are going to be set at P. And what P will be exactly, we'll see later, but it is a hyperparameter that von der Mausburg recommends, all right? And if this distance, square root of between these two, okay, if that distance is equals to the separation times the spacing. So EE set is the von der Mausberg saying like if this unit is 1 unit away or 2 units away, okay? So let's say excitatory, I believe it was exciting only its neighbors, but not its neighbors' neighbors. So in other words, the distance must be less than or equals to 2, if you remember. 2 units away, I don't excite. I only excite my immediate neighbor. So if the distance is equals to, I believe separation should be 1 or 2, right? But multiplied by the actual spacing unit, how many, in this case our spacing is 1.0, right? So because if we said the spacing is 2, then we have to scale it accordingly, right? So this is the scaling factor, but this is the von der Mausberg recommendation to say only 1 unit away, then I have a excitatory connection with that unit by a value of P. Otherwise, everything else that is not equals to the 1 unit away is 0, right? At this point, at first, WEE, everything is 0. Means no unit, no excitatory unit is connected to any other excitatory unit. Then after deciding all the distances, I can then know that only for the units that are next to each other, which is what this if statement does, set that 2 units connections to be P, equals to P, all right? And you can see, because it is set to be hard-coded as P, there's no learning that's going to be involved. It's going to be just fixed. It's a hyperparameter. Similarly, if the distance between these 2 units is less than or equals to whatever EI separation is, and that is what von der Mausberg would say, because it's inhibitory, it is going to be the same as EE sep in this case, right? It's like my neighboring unit. So I'm only going to excite my neighboring inhibitory neurons. Okay, so that's what EI sep times spacing will be, and then make that equals to R. And similarly, from I to E, it will be whatever the EI sep is, make it equals to Q. Okay, so these EE separation, EI separation, IE separations are what von der Mausberg says if it is my neighbor or my neighbor's neighbor, but not anyone else. Make those weights P, R, and Q respectively. Otherwise, the rest of those are zeros. Got it? Okay, let's make rough intuitive sense first, okay? All right. So that's if we didn't initialize any W. There are no pre-trained Ws. So, so we have to set it up. And this essentially sets up the architecture. So now we have 19 units with 19 by 169 random connection weights to the excitatory units. Excitatory units have P connections with their neighbors and 0 connections everywhere else. Excitatory units have R connections weights with the inhibitory neighbors, but 0 connections everywhere else. And inhibitory connection to the excitatory have Q weight size to the neighbor's neighbor according to the EI sep value, and 0 anywhere else. Okay? Yeah.
So the cycle when we implement the order,
Mm-hmm.
are doing 2, 2, 2, or
Sorry, wait, what?
So when we implement the order,
Yeah,
so we put 2, 2, 2.
I think we do. Let me see.
Interaction between these.
Here, I put 1, 1, 2 here. List of orders. This is going to be the determine the EI set. So this is going to be 1, 1, and 2. So if you go back here. So this is going to be 1, right? Is that right? It will take that, right? Because, yeah, see? So EESAP is going to be 1, 1, and 2. So in this case, it will be, skipped it. Okay, 1, 1, and 2. So my neighbor, and my neighbor's neighbor. That make sense? Yeah. Okay. If you do 2, 2, 2, for this one, it will be my neighbor I don't excite. I only excite my neighbor's neighbor. Right? Got it? Yeah, yeah. Okay. Yeah. Please remind me, or if anything is not clear, let me know, because also there's so many things happening, so I need refresher as well. Okay. It is clear to me, but it may not be clear to people who didn't write the code. I wrote this code, so, but I've written it a long time ago, so sometimes I need cues to remember. Okay, so that's what the order does now. I said it becomes clearer as we go along. Order tells us which is the von der Mausberg setting, as to how many units you want for the array that you want the excitatory to have influence, excitatory to inhibitory to have influence, and inhibitory to the excitatory to have back influence. And in the example later, you'll see below, I set it order to be 1, 1, 2, which means that, and you'll see EESEP, EISEP, IESEP are correspondingly order 1, 1, 2 later on. And so if it's 1, 1, 2, which is implementing the von der Mausberg setup, it effectively means to make P for my immediate neighbors, R for my immediate inhibitory neighbors, and Q for my neighbors' neighbors if I'm inhibitory neuron, for my neighbors' neighbors in the excitatory layer. Okay, so that's what all this one means. And note, it is based on the Cartesian definition of the distance. All right, so this spacing has a Cartesian value. So you can say 1 is equal to, let's say, 1 millimeter. And then these will be have millimeter unit, okay? Or micrometer, micron, okay, if you want. Okay, so this is critical, right? So this is the first part. If we didn't have any pre-trained weights, this sets up these arrays with the values. And critically, 19 to 169, the input to excitatory is initially random. Okay, if there are pre-trained weights, then just copy them in accordingly. Okay, so then now we start with the actual training cycles. And to do that, we have to set up a bunch of empty variables first. You will see that I have this WIET because we're going to have iterations. So the weights over time, okay, and the activity over time. The excitatory activity, the inhibitory activity, excitatory, inhibitory, the overruns, okay, and over iterations. All right. So because we're going to do batch updating, what is going to happen is we're going to give it a stimuli, and then it's going to run iterations, okay, like for 20 times, and then it's going to settle, okay, and then we're going to do another cycle 20 times, and it's going to settle. Each of the 20 times is one run, okay, but each has 20 iterations, has 20 iterations. So we need basically an ASDT and ASE because there's two sort of wrapping cycles happening in this loop. You'll see that come out later. Okay. So then, and then some other. This is the activation state. So it'll be the A, which is equals to the ReLU of the pre-activation state. Pre-activation state is actually this one, signal. Sig E, sig I, okay? These are the A prime, which is the sum of the weights times the input, okay? That's sig E, sig I. Sig E, sig I are the pre-activation state, and which we also call the output signals from the upstream layer. They feed into the ReLU, and that will give you the activation, which are the AS, E, ASI accordingly. Okay? So that's why we have all these components. And then we have some other indices that will play out later. We'll see them come into play later. All right, so we can specify how many runs we want to do this. Perhaps we want to train our network only for 50 times, or we want to train it for 100 times, or we want to train it for 1,000 times. That's the run. We want to have these training cycles over 100 runs, 1,000 runs, 10,000 runs. That's this outer for loop first. So for in each run, we initialize the excitatory state pattern variable. Okay, first make it empty. Then we actually start with a normalization, because remember, at first already we said random uniform values, right? In the initial 19 to 169 array. These random numbers, which range from 0 to S, could be big or small, right? Whatever S is, okay? So we want to start out already. The first thing is normalization. Although conceptually we say like we train and then we normalize, but in the code we go ahead and normalize first anyway, because basically that's what it is. Whatever weights you have right now, normalize it, train, normalize it, train, normalize it, right? It's the same as I didn't start out there. I said train first, then normalize, train first, then normalize. Here, we assume that this training is continuous. So for a random set of weights, we normalize it first, then we train it, and then we normalize again. So the normalization happens here first, and this is the normalization, which is this implements that 19 divided by 2 function that we had in the paper and last week's lecture, okay? You'll see that that's what this does. So now the weights, whatever range they are, have been adjusted, okay, so that they fit they are more balanced given the range of the weights that are actually there, okay? Then now we start. There are 9 input patterns. So for pattern 1, the first pattern, we will make the input pattern equals to that pattern. So input, let's say pat is 0. So input P is equals input number 0. So it's the vertical line, okay? The 19-bit word in a hexagonal, with a hexagonal projection that we know of. So then we're going to make ASE and ASI first equals to zeros according to the number of units, which is 169, okay? So ASE is going to be a 0 vector with 169 by 1 size, and ASI is also 169 by 1 size, okay? Then we do this number of iterations, which I said, I think VDM wants us to do 20. So in other words, this is going to be a scalar number 20, okay? So for count in 20 numbers, okay, from 0 to 19, do this. For each iteration of the ASE, append a new ASE copy. You see this because then it will log as ASE changes. It will have how ASE changes over the 20 cycles, and ASI as well. Compute the excitatory output signal. So compute sig E, okay, which is the ReLU, I'm getting confused. ASI is the pre-activation state, and sig E is the ReLU the ReLU nonlinear state. So let me backtrack in case we were confused, okay? Sorry if I confuse you. This should be the pre-activation state. This is the activation state. So yeah, because it's the output. It's whatever you have in the pre-activation, then you apply the ReLU, then you get the signal that comes out. Okay? Hope I didn't mess you guys up there. Okay. Right. What I said was flipped the other way around. Yeah, so that's why you see now for each of the excitatory units, the output is equals to the pre-activation minus the threshold, right? And then depending on whether that value is bigger than 0, take the maximum of it. And that's ReLU. Maximum of the difference versus 0. So if the difference is negative, then 0 will win. If the difference is greater than theta, if the difference is positive, which means that the pre-activation state is greater than theta, then it will the signal will be that difference in the value. Okay. So then for inhibitory units, ASI is equals to the dot product of the E to I weights by the signal that's coming from the output of the excitatory units, and therefore the output of the inhibitory units is going to be again the ReLU of the pre-activation input states minus theta versus 0. Okay, so you think about that. We're computing all these excitatory outputs and then inhibitory outputs, all this, okay? Then we append it, so we log it, so we have like how all these values are changing over time. So IP append, excite append, inhibit append, all these things you can, there will be outputs from the return values from this function, and you can probe it and poll it later. And this is the critical line here. For the first iteration, what we have done is we have, for that input, the first run, first iteration, the vertical line, we have pushed forward, fed forward the activity times the normalized weights to compute the activation state, the pre-activation state and the output, and the pre-activation inhibitory state and its output, so that then we can see how the activity of the excitatory layer, which is equals to the dot product of the input plus the dot product of the input weights times the input plus the dot product of the excitatory recursion, which remember we set it as P for the neighbors, right? Times the output of my neighbors, sig E, minus the dot product of WIE, which we set as R, which has, and then the activity of the inhibitory neurons, the output of the inhibitory neurons. And we have this plus this minus this. And that determines the new pre-activation state of the excitatory units in the excitatory layer. Then we impose a then we record it as the maximum. You'll see why this is needed, because we will use this later for some metric. Okay, the maximum of the activity minus the new activity minus the original activity. We will use that later as an index. But this now the pre-activation state of the excitatory layer will be equals to the new, or a copy of this updated, after adjusting for the recurrent excitatory information and the inhibitory information. All this is now updated to be the new excitatory pre-activation state. You can see this is happening within one iteration. And so it will do this, as I said, this was 20. It will do, for the vertical line, it will do this sweep 20 times. Okay? So there's no weights updating at this point. It is just waiting for, the weights are fixed, but we let the inhibitory contribution play itself out for 20 iterations. That's how it works first, okay? This is very important to appreciate. So let me iterate again. The first input comes in. They already have some random weights, okay? So the input that comes in goes to the excitatory layer, and then the excitatory layer to the inhibitory layer, which we have already fixed those P, Q, R values of the connections. And so then this activation, pre-activation, and the ReLU nonlinear activity and mutual excitation inhibition happens for 20 cycles, or the number stabilization iteration. So stabilization cycles, 20, in this case 20. Then after it has stabilized, and each time we make the excitation pre-activation state the new one. So there's going to be 20 replacements of this ASE value. Okay, but we do log the ASDT at that time. Okay, after 20 cycles, you can see this one is coming out of the loop. Right? Yeah. This is the 20 cycles ends here. So this one, after it's finished, the 20 cycles, then log it, append it into this variable. So maybe we want to see it later. Okay. And for the pattern as well. Okay. And then after that, so we have, okay. So after this 20 cycles, we have for this vertical line, 20 cycles. So we have a pattern activity, the pattern pre-activation state activity. And then, so this is called batch updating, right? For this pattern, after we have done whatever we need to do for 20 cycles, then we take the final excitatory sig-E, the latest one, okay? And we do a outer product. This is the auto-encode. The input pattern with the output of the sig-E, right? And we, this is the H here is the learning rate, eta, okay? So you do the auto-encode qualified by the learning rate. You add that to the actual original P of the inhibitory to the excitatory weights, the original inhibitory to excitatory weights, and then the new inhibitory to excitatory weights incorporate the auto-encoded part after the 20 stabilization cycles. That's all this chunk here, okay? All right. Takes a while to sink in, okay? You have the code, you can go through the loop slowly, okay? But that's what's happening. Then, after that, we do it for the next pattern. So then pattern number 1, we do the oblique one a little bit. And we do it again. We set things to 0 again. But remember our weights have been updated. So then we let the stimuli stabilize again, okay? And then we append the new weights that are learning. Then we go to the next pattern, stabilize, do the weights, and then next pattern. And we, so cycle, if essentially, if the stabilization is 20 and we cycles, and if we have 9 patterns, then it's 9 times 20 loops in total. After that, we will then add the real weights, WIE, okay, plus the pattern weights. Okay, so this is batch updating. So basically, we learn weights for each pattern. Then after that, we update the all these weights to the network weights. And then after that, we update over runs. Remember, if you say you want to train and do these pattern by 20 stabilization cycles, you want to do it one time only, or you want to do it 10 times, or you do it 100 times. It's loops within loops. We will append each performance variables after each loop, and then we return a whole bunch of variables here. Okay? All right. So now, essentially, that's the architecture, the learning rule, and the activation function all coded in just this one function. So unlike the backprop and the hop field, where we split the training and the testing and all that, this simultaneously trains and it drives the activity. It's actually closer to the way our neural networks work, right? Our neural networks don't just get trained without activating to be tested. Our neural networks are being trained and tested all simultaneously all the time. So actually this is closer to it. In one thing, you are both training but also exciting, having it give output. And from its output, it's also kind of self-training iteratively. Okay? So you have to kind of go into it. It's very complicated because it's like you have to take your perspective, like you are the neuron, and then they're like, oh yeah, I'm both being trained, but also I'm giving you my answer at the same time, okay? Which is more realistic. Okay, so here, number of, so 20. It's a hard parameter. Again, this is recommended by von der Malsburg, okay? Feel free to change all these parameters if you want, but I'm just using the numbers that are recommended in the paper. Okay, so this is the VDM function, okay? And if you play it, you will have the ability to now test it and evaluate it. So this is the first instance of training here to implement the code. We have all our definitions set up now. And so I'm going to show you how this plays out. So we have our input, which is the vertical, oblique, horizontal, so-called 9 orientations as the inputs. My W is set up, it's not pre-trained. So because it's not pre-trained, I only set up the sizes. W is a vector at first of the sizes of the input, 19 units. And the excitatory layer has 8 columns by 29 columns. Okay? So I guess I should put this here to help people. Okay? Number of input units. Okay? Number of rows. E rows. Number of E columns. In hexagonal, in the Cartesian transformation. So there's 8 by 29 will give me, right, 8 by 29, 8 rows, 29 columns will give me this. Okay, so that's what this W initial setup does. Okay, so P is, as VDM von der Malsburg recommends, P is hard-coded at 0.4, which is the E to E weights, the recurrent E to E weights. Q is hard-coded at 0.3, which are the E to I weights. R is 0.286, which are the I to E weights. And S, which is the normalization factor, the cache, is coded as 0.25. It is essentially the maximum initial strength of the I to E weights. Okay, you are having a kind of an upper bound there. But you normalize according to that, right? You normalize it so that whatever random number you have is normalized to that. H is the growth rate or the learning rate, right? The eta in the learning rules. Theta is the threshold of the ReLU, okay? And the order, which is the radius for the influences of the excitatory to excitatory, excitatory to inhibitory, and inhibitory to the excitatory. The radii are 1 unit away, 1 unit away, or 2 units away, respectively. They will be used in the code multiplied by spacing, which is the actual distance factor. So if it is 1 unit away and units are 1 millimeters apart, then it is 1 times 1. But if it is 1 unit away and units are actually 2 millimeters apart, then it is 1 times 2. Then when you implement it, it will be 2, 2, 4, right, in terms of spacing distance size. And here we want to train it for 100 runs. T is 100, okay? So then if I implement this, you see VDMU learning, WP, RQ, HST, order, input theta, which is all these things. It will run it. And this one takes a while. It's unlike the backprop and whatever. When I click this, it takes me, it's got to be about at least 5 seconds to 10 seconds, okay? Whereas the other ones are relatively fast. This one will take a while. After it runs, it will have all these, return all these outputs. And then using these outputs, I can show you the code. So it's a plotly again, and you can visualize the weights, the I to E weights at time t, iteration number what, as a color scale heat map. And so this is what this is. And let me hide code so I can show you. At first, everything should be more or less random. You see the weights, the inhibitory to excitatory weights. So 19 by 169, right? Okay? So these are the retinal inputs, okay? So 19 retinal cells to 169 V1 cells. You can see at first, it's kind of like mostly close to 0. By the way, this is not positive, negative. This is 0 to 1, okay? So all close to 0 and a few ones, but it's not really any meaningful pattern, okay? Let me go next. Something is starting to happen, you see? Okay, can you see something? It doesn't change much after that. It's like something special is happening for this unit. All right, but then you can see also the other units are becoming more and more strongly 0 or strongly non-zero. Can you tell me what's happening? What's so special about this number, this one? There are 19 units. Anything special about this? I mean, clearly you can see this one special color. And I can tell you every time you run it, it will be like that, more or less, in this setup. Any insight? There's one unit that's very special. One input unit that's very special and has high connection to all 169 units. Nope. Okay, well, it's sort of like a bias, but it's not purposefully a bias, but effectively it might be a bias. Any insight? Yeah, exactly. And which is bias-like. Look at all the 9 inputs. There is one unit that is always on. Yeah, center. And because it's always on, effectively it's almost like a bias unit, right? Remember, bias unit is like it's always on. Yeah, so yes, but effectively we're not like trying to put a bias in there, but it turns out to be, it has that effect. Okay? And because it's always on, so it's always reinforced. Right? Auto encode. Psychologically, you could think of it that, oh, this is the centroid of this local area. So this is sort of coding that it is this part in space, and because there's only these 19 units, if you were to expand, if you were to have time and say, I'm going to make a lot of 19-unit patches to encode many orientations in my whole field of view, the center defines that location, as opposed to the next 19 patches. The 19 patches will each have their center. So those will be always on with respect to the 169 unit, right? Think about that. So the center is very special because it encodes that this is this location in this space. And then the others are telling it like, well, relative to the center, I am going to be on or off selectively. And as we work as a team, this array will tell me, has the information about what's happening in this, based on this center, what's happening around the center. Okay? All right? See this insight. So you see, with this visualization, you can see that, and you know, at first, it's random, effectively. Okay? But you can see a trace of it coming out already, but just not yet. But then after I train it for 100 times, it becomes very, very clear. The weights become very, very distinctive. Okay? So you can have this kind of tool to visualize how your weights are changing over runs. This is run 0 to run 99, 100 runs. Okay, here's another visualization. I can evaluate the excitatory layer. So excitatory layer, E layer, okay? And I'm going to say iteration 0 again. And I'm going to use the vertical line as the input. Okay, this is the first run, okay? You can see some clustering, but you can see some stray dots active. So in other words, after training like 20 iterations for stabilization and training it over the 9 different inputs, this is the excitatory layer activity to the 9 inputs. Let's see if I can make it smaller. Yeah, so it's easier to visualize. Okay, all right. So at just run number 1, this is the response to vertical line, oblique a little bit, more oblique, horizontal, and then going back towards the vertical line. You can see there is some clustering, but you do see some, stray dots and all that, like things like that, right? Okay, let's compare it. Okay. See, much neater, correct? Very little of the dots. If there are, it's because it's at the edges, okay? Very nicely behaved. Essentially, this is VDM already. You show that there is local clustering and it's selective. So each neuron really only likes its own orientation. You can't really see it yet. You might need to have color, so you can tweak the code so that you can cycle from all the different stimuli here, 9, and don't cycle, but put them all on top of each other. You will see, like, if it's red, blue, green, like that, you will see the spindles come out. And they will come out at, I would imagine that even at run 50, you will already be more or less pretty well behaved. Okay, so this is this visualization tool. Okay, so this is the inspection. So if you want to say, you ask me, how do we evaluate the model? How do we know that we are? Well, first, you see this, and if you see visually that, yes, it seems to be making sense as we expect. Okay, then the next question is, how do I quantify these things? So you can, because you have this visualization, you can do sensitivity. Oh, I didn't have that here. But yeah, we'll do that maybe in the lab next week and all that kind of stuff. But from here, because you have the activity response, then you can do like, have a plot of, for any one of this neuron, like say let's take neuron number 1, unit number 1 here, or unit number 5, I forgot. And you ask, does it turn on? The probability that it turns on across all the 9 input states at iteration 0 versus the probability that it turns on to all 9 input states at iteration number 99. You will see the probability should drop, or the distribution should be, it should only turn on to one of those states, but not all 9 states. Not all 9 input states. And so that's one way to evaluate. Okay. Another way to evaluate is you find a way to draw a line through here and you pick these coordinates. Okay, this is a bit more difficult. And then you can plot like for one input state, again, training 0 versus training 99, is it like there is some sort of the manifold, right? It likes the orientation or it doesn't like the orientation, things like that. Okay, and then you draw a line this way, you draw a line this way, you draw a line this way, and you see that at iteration 0, you might get bumps, and then at iteration 99, you might get fewer bumps and or more extreme activities, things like that. So those are some tools or ways of thinking to evaluate this model. And if you show that, then conceptually that is becoming more selective. Initially, the network, all the neurons are responding, in an undefined way, non-selective way to the different inputs. After training, the neurons start to, I only like this one and I don't like the other one. And my neighbor likes something that is near to me, but he or she will, have their own preference, of course, a little bit, but we are similar. And as they go further and further away, it becomes less and less similar. Right? So that's convolution happening because of the PRQ, all this, right? Because we tell it to only influence the 112, okay? To only influence the neighbor or the neighbor's neighbor and not anything beyond. So therefore, my neighbor will be like me, right? My neighbor's neighbor will be less like me, and then everyone else far away, I don't care. Something like that. Okay? That's convolution. Okay, so that's the code. A lot to absorb, but you can see similar elements of the way to think about it from what we've been learning, the way we approach the hot field, the way we approach the back prop, okay? You can see similar elements. Architecture, learning rule, activation function. But here, we add something interesting, where the input itself has embedded meaning, and then because of the way you set up the architecture and the way you play it out, you see something interesting in all that. But I will argue this is much, much, much closer to real neural stuff than the hot field implementation that we had and the MLP. The MLP and the hot field were already okay doing something very abstract and psychologically, to test memory and to test error learning and all that. But I will argue here is where we are, blurring the gap between what is biologically what we see for real and what this neural network is, how it's performing. Yeah. Okay. Okay, so at this point, anything about the coding and the implementation? No? All good? Okay. All right, so then in that case, for today, that's pretty much it. Like I said, today is pretty easy to go through this one. Easy in a sense that the code that's just it. okay? And a lot of it is the hexagonal part, which is not actually a neural network issue. It's just a kind of a formatting of the input issue, okay? The neural network has its challenges, but it's something you just, if you take time and see, you will get it, okay? Now the challenge is whether you can do it, you can see the link between the paper directly and to the code implementation and using it, but without the intermediate guidance, like I break it into parts for you too much. Okay, I mean, I do it somewhat here in the sense I gave you the hexagonal stuff and then you can have 9 inputs and all that, okay? And general, like how to use it. But to put it into a formal argument, what's the formalization, the data table formalization, the hypothesis, and all these parts, and the replication. I leave it to you guys how you want to submit your assignments to show like you have replicated the VDM model as it is in the paper. Okay? Okay, so in that case, next week will be the final of all the actual requirements. We will just do a lab. And because the VDM is so simple, the lab also will be very simple. I think really it's more like you guys trying out, I guess I can open it so that it's not just for the VDM part, but any other backprop part that you might want to worry about. Remember your backprop is due next week, okay? The assignment 2 is due next week, midnight. So next week's lab will also be very simple. I'll probably just show you how to do the probabilistic thing and the selectivity test and all that. It's very easy. Well, it's relatively easy. And then, and that will be it for the formal class. The week after, which will be the last week of the semester, it will be more I will just talk about more generics issues in the broader field. So like LLMs, RNNs, CNNs, DNNs, and other issues with neural network, artificial or biological ones. It's more like 闲聊啦, okay? Not anything too formal, but to make a final link between what we do in class and what you all will be obviously experiencing. We all are experiencing outside of class when people talk about artificial neural networks. It seems very different, okay? But how are they different? Are they really that different? You know, how should we understand or put this all together, okay? I also emphasize that, again, this class is primarily focused on neural plausibility, the biological essence of a neural network, fundamentally, okay? Now, artificial neural networks, they don't care about, in fact, they've already kind of moved on quite far to say biological neural networks are just one kind of neural networks, and there are so many others. True, there are so many other kinds of neural networks, and their goals are different, okay? So, but this class, we're focusing the in-depth issue for those of you who are concerned about the biology part. The value of the biology part, if you want to argue, like, okay, what about, then if this is just one special case, isn't the general case more important or more like, you know, should we learn that? Yes, but the general case has so many, okay? And this special case biology is doing something very special. And there's things we haven't actually learned or know yet. And what is it, right? And we can talk more about that at the end of the last lecture. I guess, as always, when you submit the assignment, if you guys have ideas to reuse this or expand from this, very much welcome for you if you guys want to submit things like that. Those will be more interesting to me because I've seen people replicate the things over and over again for 10 years already. So, you know, if you can do something more interesting, I think that'll be very cool. For me, that makes me feel like you guys have really digested what's in this course and even being able to use it beyond that. That would be awesome. That would be great, really awesome. Okay? All right, so then for me, that's all from me today. And I guess we can end early, have an early lunch. And then if people have any other questions, informal, feel free to stay, and we can chat. But otherwise, I will see you next week. And we'll just, again, have a very light lab. And then you guys busy yourselves with answering the assignments. Okay? All right, thanks.